Welcome back, everyone. In the last video, I have solved a few previous year GATE questions. So, if you haven't watched that video, then I recommend watching that because it clears a lot of concepts. All right. In today's videos, we will be covering the inverse of a matrix and inverse of a linear transformation. Okay. So before that, I come up with a tool, very good visualization tool, which shows you what a matrix do. As we all know that matrix is nothing but a linear transformation. It transforms a given vector space, right? So I will show you how it visually look. So for example, we have this matrix 3012. We already know that what this column means. 30 is where I had landed. This is where I had landed, right? And this basically means where J had landed, right? So we need to see that what this transformation, which is nothing but a matrix, but what this matrix, which is nothing but a linear transformation, do to this vector 1 comma 1. Okay, so it will transform it. So this is a tool. I will share the link in the description below. So in this tool, you can see that we have entered this matrix, right? The same matrix 3012. So 3012. So basically 30 basically means where I had landed. So if you see this green circle, right? So this basically indicates where I had lands after the transformation. So initially the I hat is here, this green arrow, which is 10, and J hat is here, the red arrow, which is 01. So after transformation, I had landed at 30, and where J had landed, it lands at 1 comma 2. So here is that red circle 1 comma 2, and this is the vector of interest. We need to see where this vector 1 comma 1 goes. So if you see this matrix vector product, it simply says that after the transformation, this vector will go to 4 comma 2. So how it will look like, we are going to see. So there is a slider here. So if I move this slider, it will visually show me how this space, this input vector space, which is nothing but the R2 XY plane, right, is going to be transformed, how it is going to be transformed. So let me just move the slider. See, it started moving. If you see, yeah, now I am going to clear you one thing, that the in the background, if you are able to see these gray lines, right? These gray grids, these are the original. These are the input vector space, and the blue one, the blue grid is the transformed vector space. So I am moving the slider slowly, and you will see how this input vector space, the gray grid lines in the behind in the background are getting transformed. See, it is getting slowly transformed. So if you see slowly these green arrow, the I hat and J hat will land at these locations, because this is what this transformation, this is what this matrix is doing. This matrix is moving I hat to this 30 location and J hat to 12 location. So as I move the slider, these I hat and J hat will land at those position, and we will be seeing that this original vector 1 comma 1 will also be landed to its destination, which is 4 comma 2. See how this vector space is getting changed. Okay, see, slowly if I keep on moving, eventually it will be. Now finally, see, I have completed the slider. So this basically is nothing but the iteration or kind of a time thing, right? So initially it is 0. Now if you see t becomes 1. So now the I hat is at 3 0 and J hat is 1 2. So we have transformed. So if you see in the background, we have those gray grid lines. That indicates the original input vector space, which is the XY plane R2. And these blue grid lines in the foreground is the transformed vector space, and that is also R2, that is also in the XY plane, right? So this is what a matrix do. It basically linearly transforms the vector space. And you see after the transformation, the gap between the grid line is uniform. The gap between these two grid lines is same as the gap between these two grid lines. So that linearity is maintained. And also you will see that all the straight lines are preserved, right? So this is what metrics do. That is linear transformation, right? Now we are interested in matrix inverse. Okay. or linear transformation inverse. So basically, what a matrix do is inverse do opposite, right? It kind of undo the effect. So for example, if I say that what is the multiplicative inverse of 2? It's 1 by 2. So for example, if you multiply a number, let us suppose you multiply a number a by 2 and you get something. If I say that you need to undo that effect, then you get b. If I want to calculate a back from b, then you have to do multiply with the multiplicative inverse, which is 1 by 2, right? And you will get a, right? So basically, same goes for matrix as well. So inverse of a matrix is it kind of undoes the effect of the original matrix. So first of all, we will talk in terms of linear transformation. So we will first talk about inverse of a linear transformation. Then we will come to matrix. Inverse of linear transformation. All right. So first we will go with the definition. I will write down the definition and then I will explain. So a linear transformation, let us suppose T is a linear transformation. It is from Rn to Rn, right? Is invertible if there is a transformation S which is also from Rn to Rn such that S of T of vector V is same as vector V, and this is also equal to T of S of V for all V belonging to Rn. So let's break this down. What I'm saying that a linear transformation T, which is from Rn to Rn, so it is transforming the Rn vector space to Rn vector space, is invertible. It is invertible if there exists a transformation S, which is also from Rn to Rn, such that if I transform this vector V using T, I will get something. Let us suppose I am going to get W. Okay, let us suppose this is nothing but W, the vector W. And if I transform this vector W using S, then I will get V again. Okay. So it is saying that T is invertible if we have such a transformation S which undoes the effect of T. If T is doing something, then S has the capability to undo the effect. So if T is moving, let us suppose uh, if T is, this is the original vector V, right? If T is transforming this vector V to W, let us suppose here, then we have also a transformation S from Rn to Rn, which will give you V back from W. So if you apply S to W, then you will get V, right? So it is kind of the like division is the multiplicative inverse, right? So the multiplicative inverse of 2 is 1 by 2 because it is undoing its effect. Similarly, here S is undoing the effect of T. So whatever is done by T, S is doing its inverse. And same we can also say that T is also doing inverse of S. So if we are getting, if we are transforming, let us suppose uh, v using s and we are getting let us suppose a vector z, right? Then what t will do, if we apply t to the vector z, then we will get v again. So both t and s are inverse of each other, so they are doing inverse, I mean they are undoing each other's effect. So why this is important? There is one more thing which is important in the in inverse is a transformation can only be invertible if and only if the transformation is one to one, right? This is very important point. It says that a transformation can only be inversed if and only if the transformation is, sorry, is 1 to 1. So why this is important? Why this is important? This is important because let us suppose if the transformation is many to one. So what it means is, for example, let us suppose we have a transformation T, which is, let us suppose there are two vector in the input vector space V1, and we have another vector space, let us suppose V2. And the transformation T is transforming both the vector V1 and V2 to the same vector. Let us suppose it is transforming both V1 and V2 to the same vector, this one, right? Maybe it's W, which is same as T of V1 and also T of V2. Let us suppose this is the scenario, right? So what we are saying that the transformation T is transforming the vector V1 to W, and it is also transforming the vector V2 to W. Now you won't be able to go back, right? Because let us suppose now I give you W. Now, if I say, let us suppose there exists an inverse of such transformation T. Such transformation T, there exists an inverse, let us suppose T inverse, right? Now, if I apply T inverse to W, if I apply T inverse to W, now tell me whether you will get V1 or you will get V2. You don't know, right? Because T has transformed both V1 and V2 to W. Now you don't know that if you apply the inverse of that transformation to W, you are getting V1 and V2. Why? Because both V1 and V2 are transformed to the vector W. You cannot invert W to get V1 or V2. Uh, I mean, it's not possible, right? It's pretty simple. It's very intuitive because both V1 and V2 are transformed to W. Now you cannot go back from W. You don't know whether you need to go to V1 or V2 because both can transform, both can give W after the transformation, right? So that's why a transformation can be inverse if and only if it is 1 to 1. So that's why 1 to 1 is important. If it is not 1 to 1, if it is many to 1, then it's not invertible, right? Because many vectors can collapse down to one single vector. So we can only go for in the forward direction. We can only go from V1 V2 to W. We cannot go in the backward direction. We cannot come up from W to V1 and V2, right? I mean, this is not possible. So so what inverts do, it kind of do the kind of an undoing effect. So we will see this for the same example. Let us suppose this is the matrix 3012, right? We will first calculate its inverse. So right now I'm not showing how to calculate the inverse. So it's there are three ways we calculate the inverse. For 2 cross 2 matrix, it's pretty simple. So the inverse of this matrix is this: 1 by 3 minus 1 by 6, 0, and 1 by 2. So basically, the inverse of this matrix, is, its inverse is, it's 1 by 3, 0, minus 1 by 6, and 1 by 2, right? 1 by 3, 0, minus 1 by 6, 1 by 2. Now we will see, we have seen this thing that this matrix transform this and gives us 4 comma 2, right? So it's like saying that you in the input vector space 1 1 got transformed to 4 comma 2. We have seen this, right? This, see, this this 1 1, this is 1 1, and this got transformed to 4 comma 2, right? Now let's try to do let's do the inverse of it. So if you move this matrix this side, then this will become this will become this inverse, right? So this will become 1 comma 1 and 3 0 1 2 inverse and 4 comma 2, right? And the inverse of this matrix is nothing but 1 comma 3 0 minus 1 comma 6 1 by 2. So basically, by simple maths, if I apply the inverse to this output vector, I should get the input vector. This is what the inverse of a matrix or inverse of a linear transform do. It undoes the effects. So let us see, is it the case or not? So in the same visualization tool, I have this, see, this is the inverse because I just converted into float. 1 by 3 is 0.33, minus 1 by 6 is this, 1 by 2, and this is 0, but because we, in this tool we need to drag and drop, and there is no way to enter the values as far I know. So it's very difficult to get the pinpoint 0, but right now you can assume it's 0. And the input, this we need to inverse transform this vector 4 comma 2, which is the output in the first case, right? Now it become the input, so 4 comma 2, so this is 4 2, this is close to 2, 1.97. Now if you see, if you multiply, we are getting 1 comma 1, that is the input, right? This is the 1 comma 1, right? So indeed the inverse is doing the it is undoing the effect of the original matrix. Now we will see in the visualization tool. So this is the initial setup, right? So if you see this, the I hat is here, j hat is here. Now after for this matrix, where I hat lands, it lands here, 0.3 and 0. Where j hat land, it land at minus 0.16 and 0.5, right? And this is the input vector 4 comma 2. Now we will apply the transformation slowly, and you will see how the input vector space is getting transformed. So if I move, see in the background, we see the this gray grid line. This is the input vector space, and the blue one is the output vector space, the transformed one. If you see this yellow arrow, it will slowly move from 4 comma 2 to 1 comma 1. Just keep seeing, just keep checking this, and at the end, see, it moved to 1 comma 1. See, if you see the background grid lines, gray grid lines, it is at it is precisely at 1 comma 1. So if you see, if you just see how this visualization goes, it is kind of stretching the vector space, right? See, it kind of stretched the spacing between the grid lines and kind of moving forward, right? In the right direction. Whereas if you see this inverse of it, you will see it is moving in the backward direction towards left and squashing the vector space. If you see slowly the space between the grid line is getting compressed and it is moving in towards left, right? If you see the grid lines, it is moving towards the left, the this vector and the I hat and j hat vector, right? So if you see now the space between or the area has been decreased by 4, like it has decreased as compared to the original spacing, and in this scenario it has increased. In this scenario it has increased, right? So this is what a matrix inverse is doing. It just simply kind of do the undoing effect, right? And we know that linear transformation and matrices are nothing but same thing, right? So now let us suppose we will see a matrix which is not invertible, a matrix which kind of moves multiple vector to the same output vector. In this case, this transformation T, right? It is moving the two vectors V1 and V2 both to the vector W. So let us suppose we take such a vector, such a matrix. So for example, this is such a matrix. 1 0 1 0. So what it is doing, I hat remains at 1 0, but j hat has been moved from 0 1 to 1 0, right? So basically you will see this matrix is kind of squashing the vector space. This T is from R2 to R1, right? Because in the upcoming lecture you will see the rank and all. So if you see, these two columns are exactly same, so they are linearly dependent. So only one column is enough, and the rank of this matrix is 1. So this is moving the input vector space, which is R2 to R1, right? So if it is moving the input vector space from R2 to R1, that basically means it is moving a plane. It is moving an entire XY plane to a line. It is moving an entire XY plane to a line. So if it is moving entire XY plane to a line, then it is only possible if more than one vector is getting moved to the same location. So in this case, for example, if I check this 1 0 1 0, if I take a vector, let us suppose 1 comma 3, then what is its output? It's 4 comma 0, right? So it is moving the if you see, it is So 1 comma 3, maybe 1 comma 3 is lying somewhere here, right? So it is moving 1 comma 3 to 4 comma 0, somewhere here, right? And this is 1 comma 3, right? Similarly, if we take another vector, if we take another vector, if we transform another vector with the same matrix, let us suppose 3 comma 1, so its output is also 4 comma 0, right? So 3 comma 1 will lie somewhere here. This is 1 comma 3, maybe 3 comma 1 lies somewhere here, right? And 3 comma 1 after transformation is also here, 4 comma 0, right? So this is same as if you applied a times the vector v1 and same as a times the vector v2, right? So this is vector v1, this is vector v2. Right, so this is the perfect example for our case where the matrix is moving more than one vector to the same output vector. So it is squashing the vector space. So let's see how it visualize. So if we see this, so uh, the matrix is 1 comma 0 1 comma 0. So I had will go to 1 comma 0. So I will just drag and drop. See, this is how you drag this. I am just dragging it. See, I dragged it at 1 and 0.01, which is close to 0, right? Now I will drag this one. I will drag this one to 1 comma 0 itself because the matrix is 1 comma 0 1 comma 0. See, 1 0 and 1 0, nearly 1 0. Now I will take this vector to 1 comma 3, 1 comma 2.97, which is close to 3. So if you see the output is 4 comma 0, I mean it's not exactly 40 because the values are not exact, but yeah, you can assume that this is 40. Now if I see, if you will see this input space will be squashed to a line. So see, this is getting squashed slowly, this is getting squashed. See, if you see in the entire diagram, the I hat remain at the same position. It's just that the J hat is moving toward the I hat, right? The J hat is moving from 0 1 to 1 0. So it is you are kind of wrapping this R2 space into a line, basically the x-axis. And similarly, this vector 1 comma 3 will slowly move to 4 comma 0. You just see this how this J hat is moving from 0 comma 1 to 1 0. It is kind of taking the entire R2 space xy plane and wrapping into the line, the x-axis. See how it is moving. See the red line slowly it will move to, and now see from here onward it will be clear to you how the space is getting wrapped. See, 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 and now see everything is getting wrapped. And here is your input vector 1 comma 2, which becomes 1 comma 3, which becomes 0 4 comma 0. Right, now we will check the same thing with 3 comma 1 as well, the another vector 3 comma 1, and you will see it will be at the same 4 comma 0. See, this is 3 comma, okay, 3 comma 1, close to 3 comma 1. See, it is also getting wrapped to 4 comma 0. So now see, slowly it will move to 4 comma 0. We are moving right. Now if I ask you the question that is there exist a inverse of this matrix such that I can move this transform vector 4 comma 0 to 3 comma 1? No, it's not possible because both 1 comma 3 and 3 comma 1, both the vector 1 comma 3 and vector 3 comma 1 are moved to 4 comma 0. So how you are going to tell that 4 comma 0 will go to 3 comma 1 or 1 comma 3? You don't know, right? You don't know that how you end up at 4 comma 0. 4 comma 0 could have been given by the vector 1 comma 3, or it could have also given by the vector 3 comma 1. Now you cannot go back. You don't know that from which vector you came to 4 comma 0, right? So if you know that from which vector you came to 4 comma 0, then obviously you can go back from 4 comma 0 to that vector. But right now you don't know because this linear transformation or this matrix is kind of moving multiple vectors or more than one vector to the same output vector. It is squashing the input vector space. So you don't know. So in this scenario, the inverse doesn't exist, right? And in the upcoming lecture, we will see that there are many ways to find whether the inverse doesn't exist or not. One way is to check the rank. So in this case, the rank, the original dimension of the matrix is 2, but the rank is not 2, it's less than 2, it's 1. And because the two columns are linearly dependent. So it's not invertible. There is another way of checking it using determinant. We will see in the upcoming lecture. All right. So this is the visual interpretation. Right. I will show you one more algebraic way that why inverse is not possible in this case. So for example, let us suppose we for this transformation T, it is moving the two vector T v1 and T v2 to the same output vector, right? So T times v T of v1 is same as T of v2, which is W, right? Now let us suppose let's suppose S is the inverse of T, so S is T inverse, right? So if you apply S on both side, if you apply S on both side, right? Now, because S is the inverse of T, and I will just show, we know one property that A times A inverse is identity matrix, which is same as A inverse times A. So if you multiply a matrix with its inverse, then you will get the identity matrix. And identity matrix is nothing but it's like it do nothing. I mean, it's just like we have 1 as the multiplicative identity. We have 0 as the additive identity. What is additive identity? So, for example, you take any number x, you add the additive identity, which is 0, you get the same number x. So, it is doing nothing. So, it is the additive identity. Similarly, 1 is the multiplicative identity because if you multiply 1 with any number, you get the same number. Similarly, I is the identity matrix. Basically, it does nothing. If you basically multiply I with any matrix A, you will get the same matrix, right? So because A and A inverse is undoing the effect of A. So if I multiply A with its inverse, I will get the identity matrix. Basically means I did nothing. I first applied A. Uh, it will go in the opposite direction basically. Okay, so I first did A transformation A, then I did the transformation A inverse. I undo the effect and I get I, which is identity matrix, which says that we did nothing, right? So because S and T, I just assume that S is the T inverse, so S and T will result in identity matrix. So basically identity matrix do nothing, so we will end up with the vector itself V1 and V2, right? But this is a contradiction. This is contradiction. Contradiction. Why? Because this is saying that v1 and v2 are the same vector, but v1 and v2 are not same vector. They are different vector. v1 is 1 comma 3 and v2 is 3 comma 1. So therefore, if this is by contradiction, we say therefore S is not equal to T inverse. So if S is not equal to T inverse, so we there exists no such S, right? So T inverse doesn't exist. Okay, all right. So this is the inverse of transfer linear transformation. Now we will see inverse of matrices. Inverse of matrices. So it's same because if you have seen my previous lecture, I already told that matrices are nothing but linear transformation. Linear transformation are nothing but matrices. So linear matrix is a way of representing linear transformation, by the way, right? So you can simply say that if matrices are linear transformation and linear transformation of matrices, then you can say that invertible matrices is nothing but it implies invertible transformation and vice versa. It's a bidirectional implication. That is invertible transformation also implies invertible matrices. All right. So you can simply say that all invertible transformation are indeed invertible matrices. Why? Because all transformation are matrices, so all invertible transformation are also invertible matrices. So every invertible transformation has a corresponding invertible matrices. So I can summarize this as invertible transformation and invertible matrices are exactly same. All right. So in the previous lecture, I have told that transformation is a geometric way and matrices is a algebraic way of representation, right? So invertible transformation is nothing but uh, uh, this is geometric, geometrically representation, and this is algebraically. All right. Okay. So I think that's all. I maybe in invertible matrices, yeah, I just need to cover, uh, tell one property that a matrix A is invertible if there exists a matrix A inverse such that A times A inverse is I, or A inverse times A is I, where I is the identity matrix, right? So, see, I think it is very much clear to you that what are inverse of a matrix or inverse of a transformation. The long story short, cut to short, is that inverse of a transformation or invertible matrices are doing undoing the effect of the original transformation or original matrix. If the original matrix has moved a vector to a particular space, sorry, to a particular vector, if the original matrix A has moved the vector V to W, then if you apply the inverse A inverse, given that it exists, if you applied A inverse to the output vector W, you will get the original vector V. Right, it is very much similar to what we see in the multiplication, right? So you multiply a with 2, you get b. Now you multiply b, which is the output, with the multiplicative inverse of 2, which is 1 by 2, you will get the original number a, right? So this the inverse is nothing, it's very intuitive from the name itself that it is reversing the effect, right? And one important thing which we have seen is that if the transformation is moving the input vector space from higher dimension to lower dimension, right? For example, if t is moving from Rn to any dimension Rm, given that m is less than n, then t is not invertible. In this case, t is not invertible. T is not invertible. Right? Because T is moving from Rn to Rm and M is less than N. So you are moving either from R3 to R2 or R2 to R1 or R100 to R99. Doesn't matter. If you are moving from a higher rank to a lower rank or higher dimension to a lower dimension, then it's not invertible. And we have seen why. Because if you are moving from a higher dimension to a lower dimension, if you are moving from R2 to R1, then see R2 has more vectors as compared to R1, right? Although both R2 and R1 has infinitely many vectors, but R2 has comparatively more vectors as compared to R1 because it's a bigger space, right? So if you are transforming from a bigger space which has more vector to a space which has less number of vectors, then in that case, it is sure that many vectors are getting mapped to the same vector, right? So in this case, a line of vectors will be mapped to this 4 comma 0. It's not just that these two v1 and v2 is getting mapped to 4 comma 0, but an entire line of vectors will be mapped to 4 comma 0. Right. So, because it's not one to one, it's a many to one function, right? You are mapping many vectors to the same output vector, then there is no way to go back. You cannot get the original vector back. Okay. And we have seen that using this example 1010 right here. So I think that's all for today's video. I have explained you the concept of inverse. It is very important. Inverse visually we have seen what a matrix do, the transformation, what inverse is doing. Okay, and what is happening when we are moving from a higher dimension to a lower dimension. Okay, in the upcoming lecture I will be covering determinants and rank and all. Okay, so. That's all for today's videos. If you like my video, then please like my video. If you like my video, then please subscribe my channel, share my videos. Do comment if you need more clarity on any concept. Okay. Okay. See you then next time. Bye.